Alright folks, we are now in study area number 2. Okay, we're in study area number 2. We're going to be talking about primary bonding. Now, what is primary bonding? Now, primary bonding, there are 3 types of primary bonding. Okay, so primary bonding, so there is something called primary bonding, and there is something called secondary bonding. Okay, so there is primary bonding and secondary bonding. Now some of you know what primary bonding is. It's like, for example, ionic bonding. Okay, then you have probably heard of something called metallic bonding, and there is something else called covalent bonding. I think the most popular would be covalent bonding. All right, so these are called primary bonding. So primary bonding generally it's between atoms. Okay, that's very important. It's between atoms. Okay, now secondary bonding, at this moment I want to tell you, maybe in high school you have heard it as when the walls forces. Okay, maybe you heard it as van der Waals forces, but in these chapters we'll be talking more detail about it. Now secondary bonding, on the other hand, is between molecules. Okay, and so and since we talked about molecules, I hope you remember molecules is only for covalent compounds. Okay, so by the time I finish this chapter, this part here, you will understand everything that I've just written here. Some of you may understand this, some of you may not, but this is what it is. Okay, so ionic, metallic, covalent are called primary. Van der Waals forces and everything else which falls under van der Waals forces are called secondary bonding. Okay, so hopefully at the end of today's class you will understand this better. Okay, let me erase this off. Okay, that's good. Now, first and foremost, before a chemical reaction can happen, okay, the reason why chemical reactions happen, right, it's the same reason why all of us live, what we want in life. So we want to be, we humans, I think, what we want stability. That's important, right? We want stability. So in whatever we do, whether we are studying or we are working or we are living, we want stability. We want to be stable. Sometimes when there is instability, then you can't go to school, you can't study properly, you can't work properly, you can't live properly. So we want stability. So this whole idea of stability comes from the atoms as well. So atoms have something, they follow a rule which is called the octet rule. Okay, the octet rule. So in chemical reactions, what atoms do is they try to do one of two. So let's say you have an atom. Atom will lose all its valence electrons, or will gain electrons into its valence shell. Okay, it can do either one, right? It can either lose all of its valence electrons, and if he does that, we call these people metals. And if they gain electrons into their valence shell, we call these people non-metals. Okay, that's what we do. We call them non-metals. So non-metals will gain electron into their valence shell. Meanwhile, metals will lose all of their electrons in the valence shell. But the objective is the same. The objective is to be octet. That's the objective. They want to be octet. Okay, they want to achieve an octet configuration. Now, the word octet basically means 8. To have 8 electrons in their outermost shell. Okay, to have 8 electrons. So how does this happen? So like some of them, like in the case of lithium, they just end up being duplet. But let's look at an example. Let's look at sodium, right? Sodium. As far as we know, sodium is 1s2, 2s2, 2p6, 3s1. Okay, that's sodium. And at this moment, you should know that this is the valence shell. Okay, this is the valence shell. So metals, their valence shells are ns1, ns2, ns2, np1. These are their last shells will be like this. These are metals. So in the case of these metals, what they do is they lose all of their valence electrons. All right, so like this guy is from group 1, this is from group 2, this is from group 13. Okay, so what happens is they lose all of their valence electrons. So let's see what happens to sodium when he loses his valence electron. So sodium, when he loses his valence electron, becomes 1s2, 2s2, 2p6. So now it becomes a positive ion. Now you see this is the new valence shell, right? This is the new valence shell because there's no more other shell after that. And if you count these atoms, electrons is 2 plus 6, this is 8. So this is why how sodium becomes octet. And having a completely filled outer shell, makes it very stable. Okay, has a completely filled outer electron shell is the same as stable. Okay, it's very stable. So let's look at somebody else. Let's look at chlorine, for example. Let's look at chlorine, right? So if you look at chlorine, chlorine started off as 17, 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so those guys who are ns2, np2, ns2, np3, ns2, np4, ns2, np5. Okay, all of them are non-metals, including this guy ns2, np6. So but you see this last guy, this guy belongs to group 18. So he's already octet. He has 2 plus 6, 8 valence electron, octet. These are all non-metals. So non-metals, if they want to be stable, they will need to pick electrons up. Okay, like here, in this case, it just needs to pick 1 electron up to become 6, complete p6. Okay, to complete the p subshell. Here you need to pick 2 electrons up. Okay, let's make this bigger. Then you need to pick 2 electrons up to become a complete p shell. Then when it comes to p3 will need to pick 3 electrons up to become 6. Okay, and then normally p4, right? P4 will normally share. This guy needs to share electrons. Needs to share 4 electrons to become stable. So this group 14 usually shares. Okay, usually shares. Meanwhile, the rest of them, they can pick up, or they can share. So the moment they share electrons is called covalent. All right, the moment they pick up electrons, they're covalent. But the moment the moment they share, they're covalent. But the moment they pick up, they are called ionic. Okay, they become ionic. All right, let's come back to this again. So what what chlorine does is chlorine ends up picking an electron up, maybe from a metal, and it becomes like this. 3p6. Okay, so now chloride is octet. So if you look at the last shell over here, this last shell now is completely 8. 2 plus 6 is 8. So it's an octet shell. Okay, so this is the whole purpose why they undergo this whole thing, to become stable, to become octet. So then brings us to the first primary bonding, which is ionic bonding. And I think you guys have heard this before. Ionic bonding is basically like what we just saw just now. When a metal becomes positive by losing electrons to a non-metal, yeah, so there is an automatic attraction. They get attracted to each other, right? They get attracted to each other, and the moment they get attracted to each other, this attraction is called ionic bonding, right? Ionic bonding. So ionic bonding is normally called is in high school. Yeah, here we go. Is electrostatic forces, right? Electrostatic. That means is electro means electric, static means not moving. So a static force is holding things together. So it's like when a metal sees a non-metal, says like, hey, do you want my electrons? And then loses the electrons to the non-metal, and one becomes positive and the other one becomes negative, and automatically there is an attraction between them. Okay, there is an attraction between them. So that is ionic bonding. So in an ionic bonding, normally the structure is like this. Is ionic bonding is not just made up of one positive ion and one negative ion. It's not made like that. It's made with billions and trillions and trillions and trillions of positive and negative ions. And these positive and negative ions, they are all arranged in such a way. Okay, so if I represent, okay, so let's say positive ion, right? Then you have a negative ion, then you have a positive ion, you have a negative ion, positive, right? Then next to the positive will be a negative ion, positive, negative, positive, negative, and then positive, negative, positive, negative, positive. Okay, I'm going to lose my head doing this. And let's do one more. Let's do one more. What color? Okay. So negative, positive, negative, positive, negative. So what I want you to notice here is this. Okay, I want you to notice this. Okay. Around every positive ion, right, you'll see it's like if you take this positive ion here, you see there's a negative here, negative here, negative here, negative here. This is just one layer. There's another layer at the top. So at the top layer there'll be also negative, and there's a bottom layer. The bottom layer will also be negative. Meanwhile, if you take a negative ion, let's say, okay, this negative ion here, you see the negative ion is then surrounded by one positive, another positive, another positive, another positive. So in ionic compounds, right, every positive ion is surrounded by negative ions, and every negative ion is surrounded by positive ion. So this entire structure, okay, which after this you might see in your textbook has called lattice. Okay, they use the word lattice. Lattice basically is the same as structure, right? Lattice, it just sounds intelligent, but it's actually structure. So in this lattice, or in this structure, all of these ions are held together very, very strongly by ionic forces. Okay, ionic bonding. All right. Okay, so there you see lattice energy here, right? Structure energy. Okay. Now, it says ionic bonds have a range of 4 to 4,000. You do not need to know this. You do not need to know this. But what you do need to know comes here. This is the important part here. Right? This is the important part. Okay. So, what is the important part here? You see, the important part is this. The strength of ionic bonding, how strong ionic bonding is, it depends on two factors. All right. It depends on two factors. Factor number one is how big the ion is, right? Let's say you see, let's say how big. Okay, so let's say we take sodium ion, and then below sodium is potassium ion. Okay, and then let's say we have the same negative ion. Let's say we have chloride ion. Okay, so chloride ion is, let's say we keep chloride ion constant. Okay, constant. Sodium ion is a little bit small. Okay, so let's say sodium is small. Potassium ion is bigger. Okay, because it's in period 4. Potassium ion is bigger because it's in period 4. So apparently what happens is the ionic bond that exists between sodium and chloride is stronger compared to the ionic bond between potassium and chloride. Okay, why is that happening? Because you see, in this entire attraction world, one important person who plays the role silently is the nucleus. Okay, the nucleus. So the sodium's nucleus is attracting the chloride's electrons. The chloride's nucleus is attracting the sodium's electrons. Okay, so the further the distance between the nucleus, so when the nucleus are very far away, okay, like for example, let's say like this, right? Okay, so if you measure this distance, okay, let's just for the fun of it, let's measure. Oops. Oh, it's hung. Okay, let's say you measure the distance here, right? If you could, you see the distance here, and then let's say if it was potassium, right? Let's say if it is potassium here and I move potassium, let's say if I move potassium over here, you will notice that this distance is longer. Okay, that distance is longer. So the idea here is like this: when the ions are very small, the ionic bonding is stronger. Okay, so that's criteria number one. The smaller the ion, stronger the ionic bonding. Then criteria number two. Criteria number two is very easy. Criteria number two is, let's say we have somebody who's constant. Let's say chloride again. Let's keep chloride constant. Then you have sodium, then you have magnesium, and then you have aluminium. In terms of sizing, they are about the same. Sodium is, let's say sodium is this big, magnesium is a little bit smaller, aluminium is much smaller. Okay, but they are about the same. That's a lie, but about the same. So this carries a charge of positive 3. It has 3 more protons. This has 2 more protons than electrons. This only has 1 more proton than electron. So what will happen is, technically, aluminium, which has 3 more protons in the nucleus, will form a stronger ionic bond with chloride. Okay, for 2 reasons. One, it's smaller, and the other one, the charge is high. But let's say hypothetically, they're all the same size. Okay, let's say for the fun of it, they're all the same size. Okay, but this is plus 3, this is plus 2, this is plus 1. So the one with the higher charge will have stronger ionic bonding. Right? So that is what is written over here. A larger ion makes weaker ionic bonds because the greater distance between the electrons and the nucleus, the opposite charge ion, compared to this. Okay, so you can look here, right? Iodide is very big. Okay, iodine here is very big, right? Iodine is big. Fluoride is smaller. So you see, the total energy of magnesium fluoride is 2957, the other one 2327. Okay, and then the same thing goes with here. It says here magnesium carries a charge of plus 2 is 2957. Meanwhile, sodium fluoride, which carries a charge of plus 1, is only 923. Okay, so it makes a difference, right? Okay, so then we move on to metallic bonding. Okay, Now, metallic bonding is a bit easy but to understand, but also a bit complicated. All right. So let's say again, let's say we take sodium. All right, we take sodium. Sodium has 1 valence electron, right? It has 1 valence electron. If you remember, 1s2, 2s2, 2p6, 3s1. In metals, the valence electrons, okay, valence electrons are relatively free. They are relatively free from the attraction of the nucleus, which means that they are attracted to the nucleus. But they are not so strongly attracted to the nucleus, because that is why they get lost during chemical reactions, right? During chemical reactions, the nucleus is like, okay, you can go, I don't need you anymore. So they are there, but they also have a little bit of freedom. Okay, so how does metallic bonding come about? Now, metallic bonding is like this. You see, okay, let's say we take this picture here, right? This is an arrangement of metal ions. So, sorry, metal atoms, okay, metal atoms. So what we do is, right in the center of this picture here, all these plus signs here, this plus signs basically represents the nucleus, okay? So what is happening here is, let's say this is the electron that belongs to this guy, okay? So what is happening here is there is attraction. So this electron is always around this guy. It's always around this guy. And there is attraction here. This electron is always around this guy. And there is attraction over here, and this electron is always around this guy. Okay, so that's generally the rule, right? Generally the rule. But you see what happens is there are times where the electrons can be in the middle of two different, okay, like for example, let's say in this case here, the electron can be in the middle of these two atoms. See, this atom and this atom, this electron is in the middle here, right? So who does this electron belong to? Does it belong to him or does it belong to her? Okay, so what happens is, let's say originally the electron belonged to him. But because now the electron is in the middle, it can also come under the influence of this nucleus. And so this electron can start moving around here. Understand? But when it comes here, it can come under the influence of this atom and then start moving around here. And then when it comes here, it can move, when it comes here, it can move around here, you see? So whenever the electron is in the center of two atoms, the electron can move to any direction. So that is why we always say in metallic bonding, we say the electrons are delocalized. That means delocalized meaning they don't belong to one particular atom. They move around, okay? They move around. So if you could look into a structure of metal, let's say you had bionic eyes and you could look into a metal, what you will be seeing is, you will be seeing all of the electrons. You'll be seeing all of the electrons moving all over the place in this lattice, in this structure. It'll be moving all over the place very quickly. It's like you can't even see where the electron is. It belongs to everybody, okay? So this is called the sea of delocalized electron. Sea of delocalized electron. So this attraction between the positive and the negative, the electron, the positive nucleus and the negative electron, is what metallic bonding is. And because all of them are attracted in all directions, okay, in every direction they are attracted, this is what holds metals together, because they are all attracted to the electrons, right? He's attracted to this, he's attracted, he is also attracted, she is also attracted, everybody's attracted to the electron. And this is what keeps them together. See, attracted there, he's attracted here, he's attracted here, he's attracted here as well, here. So they are attracted in all directions. This is what metallic bonding is. Metallic bonding, the real definition of metallic bonding is the non-directional attraction between the positive nucleus and the delocalized electron. Okay, it's a non-directional. Non-directional means it can go in any direction. It doesn't have to go from point A to B. It can go in any direction. So that's what non-directional is. Okay, so that's what metallic bonding is. It's the attraction of the positive nucleus towards the delocalized electron, or towards the delocalized electrons. Okay, maybe I should use the word, maybe I should have not used this and say towards the delocalized electrons. Okay, now back to this again. The strength of metallic bonding. How strong a metallic bonding is. Okay, so how strong a metallic bonding is depends on two factors. Again, the first factor is the size of the cation, how big the metal atom is. So for example, let's say if this is sodium, okay, sorry, let me change this. let's say this is sodium, and this is magnesium, and let's say this is aluminium, because they're all in the same period, aluminium, then the same period they're getting smaller. I can safely tell you aluminium has stronger metallic bonding because it's smaller. Okay, smaller, they can pack very tightly together. That's very important criteria. The smaller you are, you can pack tightly together. And then the number of delocalized electrons that you have. So here, the more delocalized electrons you have, the stronger is the metallic bonding. So obviously, in the case of sodium, he can only contribute 1 electron. Magnesium can contribute 2 electrons. Aluminium can contribute 3 electrons. So the more electrons you contribute, the stronger is the metallic bonding. Simple as that. The smaller you are, the better. Whether you're a ionic compound or a metallic compound, smaller you are, the better. And for metallic compound, the more valence electrons you have is better. For ionic compounds, the higher the charge you have is better. Okay. All right, that brings us to covalent bonding. Now, for covalent bonding, we will not dwell so much into this because it's the entire next few pages is all about covalent bonding. But basically, covalent bonding is between atoms, and it's between non-metal atoms. All right, non-metal atoms, they share electrons. Like for example, let's say hydrogen chloride. When hydrogen and chloride makes a bond, this bond is called covalent bonding. And I want you to know covalent bonding is very, very strong. It's very strong. Don't ever think it's weak. It's very strong. It's just as strong as ionic or metallic bonding. Okay. So it is when non-metals share electrons. When they share electrons, that's where that's where covalent bonding comes in, when they're sharing electrons. But we're not going to dwell so much into this at this moment. So usually covalent bonding is, let's say, like for example, you have one atom, let's say it's not writing. Okay, let's say in the case of carbon dioxide. Okay, in the case of carbon dioxide. So how carbon dioxide forms is because carbon is 1s2, 2s2, 2p2. So carbon has 4 valence electrons. All right. Oxygen is 1s2, 2s2, 2p4. So oxygen needs 2 more valence electrons to be octet. Carbon needs 4 more valence electrons to be octet. Okay, so this is needs, right? This is needs. It needs 4. So since oxygen needs only 2, that's why we need two of them. We need 2 of those oxygens to satisfy carbon, because carbon needs 4. So what happens is you get a covalent bond. So carbon makes one bond with one oxygen, another bond with another oxygen, and it ends up making a double bond. Okay, these are called lone pairs. You may not understand this at this moment, but this is what it is. So carbon needs 4, right? So what carbon does is it makes one pair here, one sharing here, one sharing here, one here, and one here, total 4. So if I could draw it for you, it will look something like this. So carbon says, hey, I give you one, and I give you another one, I give you another one, and I give you another one. All right. So oxygen comes and oxygen says, okay, fair enough, I will give you one and I'll give you another one. And then another oxygen on this side, I'll give you one and I'll give you another one. All right. So oxygen has given 2 out of the 6 which are in their shells. See, there are 6 here, right? 2 plus 4, 6. Out of the 6, I've given 2. So I'm left with another 2 for myself. Okay, so I'm left with another 2 for myself. These are called lone pairs. Don't worry about this at this moment. So this is one covalent bond. This is another covalent bond. This is another covalent bond. This is another covalent bond. Okay, so covalent bonding happens between non-metals when they share electrons. All right. So there is this thing about incomplete octet, and then there is other expanded octet, and there is something called coordinate covalent bonding. This I will talk to you about later when we talk about the next pages, which is the Lewis structure, it comes to a very important part, this part here, shapes of molecules and so on. This is going to be very important. So that's when I'll be talking to you about all of these things: expanded octet, incomplete octet, and so on. Okay, so that's all for now. So we ended at page we're going to end it at page 36. So this goes from page at the beginning here. Okay, so here was page 31 to page 36. All right, bye.